Hello, and welcome back to Electrochemical Engineering. Today I'm going to talk about industrial electrolysis, electrochemical reactions, and redox flow batteries. Broadly, industrial scale electrochemistry. On the left here is a schematic from ESS. They're a local company located outside of Portland who have developed a process for storing electrical energy in what's called a flow battery. You can see here a flow battery has two large vessels for storing liquid electrolyte. In this case, it's water-based that contains these redox couples, iron plus 2, iron plus 3, and on this side, iron plus 2. When the battery is charged, you take that iron plus 2 here and you reduce it to iron 0 on the electrode. On the other side, during the charge process, you take iron 2 plus and you oxidize it to iron 3 plus. Then you have these tanks full of iron 3 plus and you have this electrode with a lot of iron 0 on it. You can then reverse the flow of current and get the free energy stored there back out. ESS has recently gone public and they are now scaling dramatically this technology. Broadly, industrial electrolytic processes consume about 6% of the US electricity supply. So they're very important in the electricity sector. They're used to convert raw materials into desired products. One example is the production of aluminum. We'll talk about that, the electrolysis of aluminum oxide at high temperature to make aluminum metal. That's how all of our aluminum is made. Another process of interest is called the chlor-alkali process. In this case, you make chlorine, Cl2, and typically sodium or potassium hydroxide, alkali base, using sodium chloride in electricity. This is a large process. It consumes about 90% of the electricity used in all electrolytic processes. Chlorine is an important industrial chemical for a lot of different applications. Industrial reactors frequently operate with a continuous flow of reactants and products. So you never have to, in principle, shut these down. There's a flow of reactants in and products out as current is flowing across the cell. The current density the reactor runs at is an important parameter because it determines how much product can be made for a given sized reactor, for a given capital investment. We call that CapEx for capital expense versus OpEx for operating expense. The voltage in electrolysis process, of course, determines the energy efficiency of the process. Here's a picture from De Nora, a large electrode manufacturer who makes the electrodes used in the chlor-alkali process. These are a stack of chlor-alkali cells making chlorine and sodium hydroxide. We'll talk a little bit more about how these cells are constructed. In the chlor-alkali process, the reactant stream is a purified, saturated brine of sodium chloride. Brine just means a salt solution in water. It flows continuously into the reactor. Chlorine, or Cl2, chlorine gas, and sodium hydroxide and hydrogen gas, H2, are the produced products. The hydrogen is actually typically not collected because it's not of sufficient high value, it's not sufficient amounts of hydrogen to merit collection. At the anode, you drive the oxidation of Cl- to Cl2. That's a 2-electron process. While at the cathode, you drive the reduction of water to make H2 and OH-. The standard potential for this reaction is about 2.2 volts. Now we need to think a little bit about the balance of ions flowing in this electrochemical cell. At the anode, we are consuming Cl- and we are inputting saturated brine, that is sodium chloride. In order to carry the current, the ionic current, some ions need to move across the cell. Primarily, this is going to be sodium plus transferring from the anode compartment to the cathode compartment. At the cathode, we're taking water and we're reducing it to make hydrogen and OH-. The sodium plus and the OH- recombine to form sodium hydroxide. So the catholyte, the electrolyte at the cathode, can be collected and is enriched in caustic soda or sodium hydroxide in water. Now, in a diaphragm cell, the solution typically flows from the anode to the cathode through the diaphragm. So there's some bulk flow from the anode to the cathode through the porous diaphragm. This is porous, microporous typically, and filled with electrolyte. You can see in these sketches here the concentration of sodium chloride in the anode versus the cathode, as well as the concentration of sodium hydroxide in the anode versus the cathode. In the diaphragm, you have this flow, But you also have migration driving the ionic currents, primarily sodium plus from right to left, from anode to cathode, but also Cl minus from left to right, and diffusion along these concentration gradients. At the cathode light is removed with both sodium hydroxide and sodium chloride. About 12 weight% sodium hydroxide is the output, and the Cl2 gas is about 98% pure. Now, more sodium plus is carrying the current than Cl minus or OH minus. The primary current carrier is sodium plus. In class, I'll ask you to think about in a group and articulate why sodium plus is the predominant ionic charge carrier in this configuration. There's about 44 million annual metric tons of Cl2 produced. Here's a more detailed schematic of a diaphragm cell. This is taken from the book by Fumio Hine, Electrode Processes and Electrochemical Engineering. This book has a lot of nice detailed schematics that you might find useful if you actually end up working on such technology. You'll notice here many cells stacked in parallel. We'll talk about how those cells are stacked and how that affects the performance of such a system. But first, let's consider some of the basic electrochemical parameters. We can define the Faradaic efficiency as the mass of the desired product recovered, in this case Cl2, over the theoretical mass from Faraday's law. This is equivalent to Mi, the mass of the desired product, divided by the total charge passed times the molar mass divided by Nf. So Q over Nf is the total moles of electric charge, the moles of product you expect, multiply that by Mi, and you get the mass expected of product. We can convert this into an efficiency based on a mass flow rate if we write, instead of Q, I for the current, Q per second, and instead of mass flow per second. Efficiency, Faradaic efficiency, is of course a dimensionless unit. And for chlorine and the chloralkali products, it's about 96%. I'd like you to think a little bit about what the other products can be, and we'll talk more about that in class. I'll make a few points here about Faradaic efficiency. Fuller and Harb define Faradaic efficiency as distinct from current efficiency. Current efficiency only includes the electron transfer processes, i.e., if you have an electrode and there's some electrons in that electrode and you want them to go on to A, but you don't want them to go on to B. The Faradaic efficiency for this process, the desired product would be A. The current efficiency for this example process would be the current flowing to product A divided by the total current flowing. But there could be other losses in the cell. And Faradaic efficiency, in fact, includes losses from all other processes, including transport and loss of material across the cell. For example, flow of chlorine into the cathode stream when you want to keep it in the analyte. I'd like you to think about this as well. Contaminants in the electrolyte, for example, carbonates, can also affect the process, for example, reacting with chlorine and forming other species that cannot be as easily collected as chlorine gas. Some other important performance measures are something called the space-time yield, or the rate of production per volume of reactor. So we define the space-time yield, Y here, as the mass flow rate of desired product divided by the volume of the reactor. Now that's just equal to the Faradaic efficiency times the rate of production of species. Remember, I is the current in charge per second flowing, Mi is the molecular weight of the species you're making, N is the number of electron transferred, and F is Faraday, divided again by VR. And we can rewrite this part of the equation, the current divided by the volume of the reactor, simply by the current density divided by the specific area of the reactor. That is the area of the electrode divided by the volume of the entire reactor. So IAR just equals big I over VR. The space-time yield is related to operating and capital expense. If you have a fixed rate of production of some product, for example, you can lower your capital expense by running a smaller reactor at a higher current density. But this results in larger overpotentials and therefore higher operating expense because you have to spend more for the electricity to run the cell. You can define an energy efficiency very simply. It's the Faradaic efficiency times the voltage efficiency. Same thing for a battery. The voltage efficiency is just the thermodynamic voltage of the particular reaction you're driving, divided by the actual voltage that it takes to drive the reaction at whatever rate you're running your reactor. Remember, V cell includes paying the penalty for driving all those kinetic, mass transport, concentration, and ohmic overpotentials that we continually discuss in this course. Here's that written out explicitly. V cell equals the thermodynamic voltage plus the kinetic overpotentials at the anode and the cathode, the concentration overpotentials at the anode and the cathode, and the ohmic losses in this first approximation. The ohmic losses can be written as follows. These are the ohmic losses in the electrolyte shown here on the right. You have R ohmic in the analyte. You have R ohmic in the catholyte. That's these regions here, catholyte, analyte. And then you have R ohmic here in the middle for the electrolyte that has to flow through the diaphragm. The area-specific resistances are just the distance over which the ions have to move divided by the conductivity of the electrolyte. There's one for the analyte and one for the catholyte. This term in the middle is a little bit more complicated because we have to take into account that the diaphragm is porous. So we need to multiply the resistance by the tortuosity and divide by the porosity to account for the fact that the entire material, the entire diaphragm, is not pure electrolyte. To that, we add the resistance of the metallic leads. Here's an example for a chloralkali cell running at about 3.45 volts, where the equilibrium potential is only 2.25 volts. And you can see all the different contributions to the actual cell voltage. Below here is again just the Butler-Volmer equation that is often used to describe the kinetics, in this case of the chlorine evolution reaction. So you have an exchange current density times the exponent of the transfer coefficient, the overpotential, and F and RT. We can rewrite I naught in terms of a reference I naught and make it specifically dependent on the concentration of Cl- in the electrolyte. Industrial electrolysis often involves gas. Gas evolution plays many roles in electrolysis. It increases the rate of mass transfer. Why is that? Well, the bubbles coming off the electrode can induce some turbulence in the electrolyte and actually speed up the rate that some species out here can make it to the electrode surface. But it also increases the solution resistance. The bubbles, they block the flow of ions. You have less electrolyte in the region near the electrode. Some of the space is taken up by bubbles, so the ionic resistance increases. Bubbles can also sit on the surface, particularly if the surface is hydrophobic, and that can prevent that part of the area from reacting. Approximately, we can write the effective conductivity of the electrolyte phase in the region near the surface as kappa times 1 minus Eg to the 3/2 power, where Eg is the volume fraction of gas in the gap here between the electrode and the diaphragm. In this case, this is the analyte, where you're making Cl2. You're driving this oxidation reaction to make Cl2. In class, I'll ask you to think about how to estimate the volume of the bubbles that you're forming. In the chloralkali process, something called a dimensionally stable anode has been very important. This is something that has been commercialized and sold by Denora for decades now. It's typically an expanded metal like titanium, which is coated with a catalytic mixed oxide, typically containing ruthenium oxide, iridium oxide, platinum oxide, titanium dioxide, zirconium, tin oxide. There's a whole bunch of elements that go in here. And the idea is that these precious metal oxides are susceptible to corrosion under the conditions under which chlorine is evolved. So by mixing them with chemically stable oxides like titanium dioxide, although it does not conduct electrons or catalyze the reaction, it's cheap and it prevents the corrosion of these expensive catalytic coatings, which allow for these electrodes to last for a long time. You can read a little bit about the dimensionally stabilized anode here from Wikipedia. So let's summarize here, table 14.1, 8 key variables for an electrochemical reactor. One is m dot of species I. It's the rate of production. It's mass per second, or metric tons per year, if you want to put it in those units, of the desired material. The other is the current density, little I. V cell is the potential of an individual cell. We'll talk about how individual cells are wired together. The energy efficiency is unitless. The total electrode area, A. The voltage of the DC power system. That's going to be the source voltage. M we're going to define as the number of cells that are connected in series. So M is just the total voltage used divided by the voltage across each cell. And AC is the area of individual electrodes. You can place cells either in parallel or in series. Here's an example of two designs that you might think about. One is called a monopolar design. In this design, you have an anode and a cathode. You have a separator. You have your analyte here, and you have your catholyte here. And you can flow species through those analyte and catholyte. So you have one anode here that is feeding two cathodes. And this cathode is simultaneously feeding two anodes. So if you alternate anode and cathode, you use each side of the anode as an electrochemical reactor. So you can drive the anode reaction on both sides. But in this design, we call it monopolar because it's the same reaction getting driven on each side of an anode, or the same reaction on each side of a given piece of metal acting as the cathode. You have electrical connections to every electrode. So the overall voltage is kept small. The total voltage applied is just the cell voltage. Now there's another design that has some advantages. In this case, you actually stack the cells in a different way, and you apply a very large voltage across those stack of cells. So what do you have here? The total voltage is just going to be the number of cells in series times the voltage of each individual cell, but we're only making electrical contacts to anode and cathode here on either side. So how does this work? What drives the current through this system? Well, in a bipolar design, the cathode and the anode can be on the same metal. So one side of the metal is going to be driving a reduction reaction. So electrons are going to be coming out there. And those electrons are coming from driving an oxidation reaction on the other side of the metal. So even though there's no wires attached to this bipolar plate in the cell, you're driving a cathodic reaction on one side and an anodic reaction on the other. Because these are all placed in series, we only need to apply current to the two end cathode and anode, and we can drive many of these reactions in series. The flow is still orthogonal in our analyte and catholyte chambers, which repeat along the length of the cell. The disadvantage of this type of system is because the voltage is very large. If you're pumping electrolytes, for example, through external pipes, you have to mix electrolytes, collect your product. There'll be some ionic pathways that go through those pumps, that external balance of plant, and some ionic current will flow through that. Because you're applying such a large voltage, that shunt current, that unproductive current flowing not through your stack of cells, but through an external shunt, but through an external ionic path, lowers the Faradaic efficiency of these types of designs. So you have to think about how do you engineer your balance of plant to keep that shunt current minimized. Let's also talk about flow configurations in electrochemical reactors. Industrial reactors typically flow. Reactants go in, products go out. Flow is, of course, driven by a gradient in pressure. And so one of the constraints, of course, is the energy, the pumping energy needed to drive flow. Though I'm not going to talk much about pumping energy here. Pumping energy typically increases dramatically as the gap over which fluid is flowing decreases. So there's a sort of minimum gap here. Typically it's around 100 or 200 microns over which you want to get your flow channels. Otherwise, the pumping energy can get quite large. In this case, we have parallel flow. So you have, imagine some large reservoir pipe on the bottom, and then there's a manifold which is pushing electrolyte through each flow channel, orthogonal to the input. The products are collected on the other side and taken out of the reactor. In this case, the electrolyte goes through the reactor once. But you could imagine a different scenario, a series flow scenario, where you want your products to go through the reactor multiple times. For example, to increase your consumption, your utilization of, say, some reactant coming in to get product out. So in this case, the catholyte and the anolyte go through the reactor multiple times, and you can tune that in order to get the best distribution of products, to get the best conversion for any given reactor. We define things like the cell pitch as 1 over the center to center distance between electrodes of the same type. So for example, the distance between anodes would be the cell pitch. 1 over that distance would be the cell pitch. The term AR is the electrode area divided by the total volume of the cell. It's a similar parameter to the surface area per volume term we discussed in porous electrodes, except now we're talking about more macroscopic electrochemical reactors. You can work out that it's equal to 2 times the cell pitch in these types of geometries. Let's walk through now a typical process you might go through in developing and scaling up an industrial electrolysis. The first thing you do is you take everything you learned in fall term and fundamentals of electrochemistry, and you'd take a single planar working electrode and a well-defined reference electrode. You'd measure kinetics, you'd measure mass transfer coefficients, diffusion coefficients, selectivity. You'd really try to understand the fundamental analytical electrochemistry of whatever reaction you were driving. So then you'd scale that to what we would call a subscale cell, a sandwich where you're using now porous electrodes that mimic the type of electrodes you'll eventually want to use to get high conversion, but are maybe made of the same material as the material you found to work well for the process using planar, carefully controlled working electrodes. You'd measure that under conditions where you have a lot of reactants. So the conversion, it's the amount reacted over the amount supplied. So you want to measure this now under situations where you're not using up much of your reactant. So the reactant concentration is essentially constant through this experiment. So the mass transport of the reactant is not going to limit you here. These cells are actually much smaller also than the eventual target. Once you understand this, you go to a full-size single cell where you run under conditions where you get the target conversion. So you have to change your flow rate of reactant into the reactor. So there's enough time for all the species to give you the conversion you want. You get refined polarization curves. Polarization is just the current voltage response of the cell, and you want to understand how that is affected by the utilization you want. Once you've optimized a single cell, you take an assembly of cells into a stack or reactor system, either in a bipolar or monopolar design. Let's switch gears and talk about some other electrolysis processes. Here's the Hall-Héroult process, which runs at 1,000 degrees C in molten cryolite. Cryolite is typically crystalline sodium aluminum fluoride. Melt it, it becomes a liquid at 1,000 C. And in this process, you take aluminum oxide, carbon, and you make aluminum and CO2. So one electrode, the anode, is carbon, and that's going to get sacrificially oxidized to make CO2. Okay. This is done in a carbon liner cell with carbon negative electrodes. Carbon's used for all the electrodes because it's one of the few things that's very stable and scalable to manufacture at these very high temperatures. The negative electrode is driving the reduction process. It's actually reducing aluminum oxide, which is soluble in cryolite, so reducing the aluminum 3+ to aluminum metal. And the denser aluminum metal falls to the bottom, and you have molten aluminum that comes out of this outlet port here where it can be collected. You can see the scale of these electrolyzers, and as I mentioned, the Pacific Northwest was one of the early locations where many of these were located due to the inexpensive electricity coming off of the Bonneville Dam on the Columbia River. And aluminum is still made by this process today. Before this process was developed, aluminum was one of the most expensive metals. Another area I'd like to highlight is organic electrosynthesis. There's actually few organic electrosynthesis reactions that have been successful industrially. Part of that's due to the need to purify the product from the electrolyte salts and costs and scaling. But it's become a really hot area of research in academia, and there's a lot of companies that are now trying to implement advanced electrosynthesis techniques to access products in organic synthesis that just couldn't be accessed before. But let's talk about one product that is made this way commercially, and that's adiponitrile. So adiponitrile is an intermediate in nylon. So nylon, of course, is a polymer that's used in fabric and in rope and things like that. It's a plastic, and it's about 300,000 metric tons per year is the production of adiponitrile. So the adiponitrile reaction has two half reactions. One here is the reduction of this precursor, the 2 proton, 2 electron reduction to make adiponitrile. And the other at the cathode, you're actually just oxidizing water to make oxygen. Protons go through a Nafion membrane. Here we're going to use this as a cation exchange membrane. It's selective for protons over other ions. So it selects the protons to be the primary current carrier. And this reaction is done on a lead cathode. Lead is used because it has a low activity for hydrogen production, the hydrogen evolution reaction. You can see here kind of a microscopic picture how we think about what's going on. You have your counterions, you have your precursors crowding up to the surface, you have the reduction process going on to make your adiponitrile product. Mediators can also be used in organic electrosynthesis. So in this case, you might not do the synthetic reaction you want, for example, taking an alcohol and making a carbonyl compound directly on an anode surface, but you could in fact oxidize something that's easy to oxidize kinetically, like bromine, up to OBr minus, an oxidized form of bromine, that could then go on to react in the solvent phase or in the electrolyte phase with your reactant to form the desired product. This is an example of oxidative mediators. There are many. They're soluble in water and can mediate these reactions. You can also have reductive mediators. And this review article talks all about mediators in organic synthesis. Here's an example of a cerium 4+ mediated oxidation of this naphthalene compound. As with any electrochemical process, we need to think about thermal management. The overall energy balance is very similar to as we discussed with batteries. So the mass of the system, which is soon to be constant, times the average heat capacity of the system, times the change in temperature with time, is going to be related to the heat flow in, the heat flow out, the heat transferred to the system from the environment, the rate of work done by the system on the environment, and the reaction rate times the enthalpy of the reaction. One thing you might think about is what this equation is equal to at steady state. So what does this equation equal at steady state? We won't talk a lot more about thermal management, but it's important to understand how you might need to engineer that to keep the temperature at the target temperature for a given reaction. You'll need to understand how much heat is generated and how the heat flows work in your system. Now I'm going to take a moment and talk about something near and dear to my heart, and that's electrolysis of water to make hydrogen. There are really two commercial electrolysis technologies right now at fairly large scales. One's traditional alkaline electrolysis, and this is done typically at the higher end here of this temperature, around 90 degrees Celsius, in concentrated, typically 30 weight percent KOH, for example. You have an anode. It's typically a non-precious metal anode composed of nickel or cobalt iron containing catalysts on the surface. A cathode, a pure nickel cathode, sometimes supported on carbon. And those electrodes are placed close or even on, in a so-called zero gap configuration, a diaphragm. And remember, a diaphragm is just a porous separator. Okay, and there's actually a lot of research and development needs right now in creating better diaphragms for these sorts of technology. But essentially, it has a thickness of maybe 200 microns or so, and it consists of pores maybe 150 nanometer in dimension. So fairly large pores compared to the size of the ion. So it's flooded with electrolyte, and you drive the anode reaction in strong base to make O2, you drive the cathode reaction in strong base to make H2, and of course the overall reaction is H2O going to H2 plus O2. Now this technology works quite well. It's quite efficient, but there are some challenges. One is that you need to separate the oxygen and the hydrogen from the hot KOH. And so you have to pump around these gas liquid mixtures through a balance of plant, additional apparati that are used to separate the gas from the liquid. The other disadvantage is because these pores are relatively big, if you have a pressure imbalance across the cell, if the pressure of the oxygen or the hydrogen is different from each other, you'll actually get transport of oxygen and hydrogen across the cell, and you could in principle have combustible mixtures of gases come out. Now, why would you want a pressure differential across the cell? Well, let's talk about proton exchange membrane electrolysis. It's a newer technology, really around for the last 40 years or so. It has a cathode also. In this case, the cathode is typically platinum or platinum on carbon. It has an anode, it's typically iridium oxides. And instead of a diaphragm or separator, it uses a membrane. And this is going to be, again, the Nafion membrane. Remember, Nafion has these fixed sulfonic acid groups and mobile protons. So this is a ion selective membrane that's good at moving positive charges like protons, but the negative charges are fixed chemically to the polymer, which is sort of like a bowl of spaghetti, and the negative ions can't move. So this is going to be an ion selective membrane that has very small pores. It's hydrated with water. When you make oxygen here, the oxygen has a hard time crossing over through this membrane, and the hydrogen has a hard time crossing over also. So why that's important, it allows you to compress the hydrogen at the cathode electrochemically. If you remember the Nernst equation, the voltage you apply here, or the voltage required to drive this electrolysis, depends on the pressure of H2. So if I apply more voltage across this cell, I can drive the production of hydrogen and oxygen at higher and higher output pressures of H2. So this type of system allows you to directly generate high pressure hydrogen. And the hydrogen you generate is very clean. This system runs on pure water. There's no liquid electrolyte. The electrolyte is a solid electrolyte. It's this Nafion membrane. So in this case, separating the oxygen and hydrogen from the water streams is easier because you don't have all this concentrated KOH, alkali, hot alkali, as you have in the other system. You just have hot, pure water. The challenge, though, here for the PEM systems is because the Nafion is very acidic, you're really limited to the types of materials you can use at your cathode and anode. In fact, at the anode, iridium oxides are really the only known catalysts that don't dissolve fast in this local acidic environment, leading to failure of the cell. And iridium is a very precious element. Its price is now $5,000 to $6,000 an ounce. Of course, that's going to change rapidly depending on the market. But we only mine around 7 tons, less than 10 tons a year of iridium. So it's a big issue scaling this technology unless we learn how to use that iridium really efficiently or replace it with something else. But it's a great technology because of the efficiency of the electrolysis, the ability to compress the hydrogen, the lack of crossover of O2 and H2, which makes it in principle safer, and the simpler balance of plant that you don't have to pump around liquid electrolyte. This table highlights the advantages and disadvantages of the two technologies. And you might look at this if you're interested in learning a little bit more. The other technology that I'll just mention, it's something that we're working on here at the University of Oregon, is emerging, and it's called alkaline membrane electrolysis. So the idea is very simple. You want to build an electrolyzer where you still use a membrane to separate the anode from the cathode that has very small molecular pores. It's a polymer membrane. But this polymer is going to be a basic polymer. Okay? So it has fixed cation groups, and it's good at conducting hydroxides. We call this AEM, alkaline exchange membrane electrolysis, water electrolysis. And it combines the advantages of the proton exchange membrane system with the liquid alkaline system, because now we have alkaline membrane, we have basic conditions at our electrodes where the reaction takes place. So in principle, we can use non-precious metal catalysts at both. And if we could get the performance of the proton exchange membrane system, that would be a real winner in the marketplace. The challenge right now is the performance isn't as good as we want it to be, and the durability is really far from where it needs to be. So here's some data from our group recently from Grace Lindquist showing the polarization curves of a benchmark alkaline exchange membrane electrolyzer. Here we're at about 1.9 volts at about an amp per centimeter squared, where a PEM system would be down here below 1.7 volts. So there's still a voltage premium to go up to the alkaline exchange membrane system. But the other problem is, depending on the membrane polymer you use, the chemistry you use, you see substantial degradation, even for the best membranes we've tested. So there's some reports of slightly better durability in the literature, but it's still a big problem. This loss of performance over sort of hundreds of hours that makes these not really viable. And so there's a lot of work that needs to happen to engineer the electrodes and the polymers, but we think there's a pretty clear path to potentially getting there for these systems. I want to now talk a little bit more about membrane electrolyzers generally, both the PEM electrolyzer and the AM electrolyzer. The business in these systems, much like the fuel cell systems, membrane fuel cell systems, is at these reactive zones, the anode reactive zone, the cathode reactive zone, where you really have a mixture of catalytic particles, maybe a conductive additive like carbon, and ionomer that's responsible for conducting the ions, right? Because we don't have any liquid electrolyte. We don't have any KOH or sulfuric acid to move ions around. So the ions have to be moving in these sort of blue channels here, and the electrons have to move in the red channels, and they have to meet to drive the reaction of interest, for example, making oxygen or making hydrogen. And then the product, gas, has to be able to get its way out. So you have electrons, ions, and gas release at interfaces, and we call these triple phase boundaries because you have electrolyte phase, solid phase, and gas phase. These are very complex reaction zones and really very difficult to study, especially under the really high current densities these electrolyzers work at. So there's a lot of opportunity actually both in industry to optimize and control these reaction zones, and in academia to understand them a lot better and feed that information into people making large-scale electrolysis devices. Here's an example of what one actually looks like. So here's another nice piece of data from Grace Lindquist in my group. So she took a iridium oxide catalyst layer. This is iridium oxide catalyst. This is the ionomer. This is black stuff mixed with the catalyst. This is the membrane here. And she took a device and she actually sliced it using what's called a focused ion beam under cryogenic conditions. So it's frozen, so there's water frozen in here. And you can nicely see how, in this case, the hydroxides transfer from the membrane through this porous layer. They undergo some reaction to make O2, which has to find its way out of here somehow. Of course, all these structures probably dynamically evolve under operating conditions. This is before operation. I won't show you the mess that happens after you operate these for a long time in this particular case. And the electrons, of course, have to be taken out to the current collector to complete the circuit. Another thing you can do, which is really valuable in these types of systems, and in fact, in many electrochemical systems, there's a lot of opportunities for using clever implementations of reference electrodes. This is something we've been working on in our group. Also, a very valuable analytical tool that can be applied fairly easy in industry settings also. In this case, this is a stack of an alkaline exchange membrane electrolyzer. These GDLs are called gas diffusion layers. That's what you place your catalyst on. It's a sandwich. You have cathode, anode, membrane in the middle. That's your electrolyzer. You flow water in, you get hydrogen, water out. You flow water in, you get oxygen and water out. These are called flow fields down here where the water is flowing to deliver to the cell. What you can do, this is an expanded view. Of course, it would all be clamped together in real life, but you can actually use a strip of ionomer. This is the solid electrolyte. In this case, it's an alkaline exchange membrane, but it's an ionic wire. And actually, I can attach a reference electrode to that. And that reference electrode can actually sense the electric potential right in the middle of this membrane electrolyzer. And if you want to read more about that, this is a sort of a nice schematic from one of these papers here about the use of these types of reference electrodes in fuel cell systems. So what's nice about this is you can actually tell what fraction your voltage is dropping at the anode versus the cathode, and you can tell something also about the ohmic losses in your cell if you use impedance to the anode versus the cathode versus the whole cell. So a lot of information can be obtained from these reference electrode measurements if you apply them in clever ways. And you can read about our work here from Chu Cheng, a visiting scholar in my group, in this paper. Okay, so next I want to talk about the reversible versus the thermoneutral potential. The reversible potential U, this is the equilibrium potential of the cell, E from fall term. Here is it for water electrolysis. You see that at room temperature, it's of course 1.23 volts. But as the temperature increases, the reversible potential goes down. It becomes easier and easier and easier to split water. And so, why is this? Well, this is because G equals H minus TS. So as temperature goes up, if the entropy of the reaction is positive, which it is, if you go to water to two gases, hydrogen and oxygen, the potential goes down. But the enthalpy of reaction is much less temperature sensitive. Now, operation at potentials above the equilibrium potential, but below the so-called thermoneutral potential, which is defined as the enthalpy of the reaction divided by NF, much like U equals negative delta G over NF, right? So that's the total free energy divided by NF. This is the enthalpy divided by NF. If you operate in this region here, your cell will actually get colder with time. So I want you to think about why this is. Why would the cell get colder if you operate it here? I'll have you discuss this in class, but it has to do with the entropy of the reaction and the enthalpy of the reaction together determining what delta G is. Now, if you go above the thermoneutral potential, if you drive the reaction such that your overpotentials take you higher than the thermoneutral potential, then you are generating enough waste heat from driving all those overpotentials such that the heat generated by those overpotentials is enough to provide the heat needed for the reaction. I'll just also remind you that analysis with so-called thermoneutral potentials is approximate for an open system, which is any real system, because it does not account for enthalpy of inlet and outlet streams. So for flowing in and flowing out, there's some heat transfer through those liquids that are flowed, and that leads to energy loss, typically to the environment, as you heat the reactants and collect them. Here's another example showing the losses observed in an alkaline electrolyzer. You'll see an ohmic loss, activation overpotential for oxygen, and activation overpotential for hydrogen. And you can look at how these all depend on current density. So you'll notice the ohmic loss increases with current density, but the activation losses are almost constant in this region for current density. So I'll have you also think about that and answer that in class. Why is that? Finally, I'll talk about a solid oxide electrolyzer technology. This is an analogy, solid oxide fuel cell. Very exciting technology because by operating at high temperature, you can operate at very low voltages. You get fast kinetics. You can have simple catalysts that work with negligible kinetic overpotential. The equilibrium voltage decreases with temperature. So for example, at 1000 C, you only need 0.92 volts to drive electrolysis, though the thermoneutral voltage is still 1.3 volts. The key issue, though, is lifetime and durability, and processing of ceramics is difficult. It's high capital cost, but there's a lot of commercial interest and commercial enterprise growing here that's very, very exciting. You can see for an R&D solid oxide electrolysis system, at any given current density, the voltage you need to put in is a lot lower than sort of the advanced commercialized proton exchange membrane or advanced alkaline. And that increase in efficiency lowers the operating expense. It lowers the amount of electricity you need to drive your electrolyzer. And as we start scaling these technologies, electricity will be the dominant cost of hydrogen produced by a solid oxide electrolyzer or any electrolyzer technology. Here's an example of an oxygen electrode making O2 from O2 minus, consisting of a LSC, which I think is a lanthanum, strontium, cobalt oxide on some support. You have your YSE, yttrium stabilized zirconia electrolyte. You have your hydrogen producing electrode. It can also reduce CO2 if you want. It's nickel, again, supported on YSC. And then here's a support layer where you transport your gases through. Because remember, these are not particularly robust. They tend to be fragile as ceramics. And commercialization at scale is probably coming with these types of solid oxide electrolyzers. The other electrolyzers are already at scale, and they're really growing very fast right now. Now let's go on to talk about redox flow batteries. So this is where we started with the discussion of the ESS systems. One of the classic redox flow battery systems is actually vanadium. Vanadium redox flow batteries make sense because you could have a vanadium 3-2 couple at the negative electrode. So this is the electrode that operates at a more negative potential. Well, at the positive electrode, you have the vanadium 4+ and vanadium 5+ redox couple. So there's a big voltage between this E and this E. And that difference, that delta E, makes up the cell voltage. You typically have an ion exchange membrane between the positive and negative electrodes. And you have big reservoirs of these electrolytes, and those are used to store the electrical energy. It's very flexible. This is because you separate the power and energy components of the cell. What does that mean? Well, the power of the cell, i.e. how fast you can get energy out of the system, is determined solely by the size of your electrodes or your electrode array. So power is determined by the size of the electrodes. The energy, the maximum amount of energy you can store, or the duration, or how long your battery will last, is determined by the size of the tanks. And that's very attractive for long duration energy storage. Typically, flow batteries have long cycle life compared to lithium-ion battery. You can cycle them many times because there are no solid-solid phase transitions. It's all liquid electrochemistry. But the energy density is fairly low, so you need really large tanks of electrolyte to store useful amounts of energy. So this is usually for stationary storage. It's not for this type of storage where you would put on your car. Typically, the charge and discharge rates are low compared to other industrial electrode processes, so that keeps the overpotentials low and keeps the energy efficiency high. This box highlights some of the key properties of redox couples that can be used in flow batteries. And there's a lot of R&D now going on to use alternative redox couples to the classic vanadium redox couples. For example, the all-iron flow battery of energy storage systems up in Portland area. Something useful to think about would be what the reactions and processes that happen during charge and discharge are, and how the cell voltage depends on the state of charge. Remember, these are all going to have Nernstian relationships, depending on the activity of the dissolved species. So you might think about that a little bit as we apply the concepts we've learned previous courses to this application. Here's some actual data. So here's the half reaction at the negative electrode. Here's the half reaction at the positive electrode. They both involve vanadium, so that's nice because if any of your catholyte and analyte mix by moving across the membrane, that's not a perfect separator of the two, it doesn't harm your cell. The difference in potential between the two is about 1.26 volts. So that's the open circuit potential. You can calculate that open circuit potential from the Nernst equation. So U theta here, that's our E naught from last term. And here's our activity term, with, in this case, concentrations used instead of activities, assuming a standard state concentration of 1 molar. The total efficiency of a flow battery is the energy out from a discharge divided by the electrical energy supplied during charge. And if the Faradaic efficiency is close to 1, that's the ratios of the discharge voltage and the charge voltage. And so you can see here, the ratio depends on how hard you push it. If you have very small current densities on your electrodes, then you get very high efficiencies. And if you go to large current densities, then your efficiency might drop to only about 50%. Notice the charge voltage is over twice as high as the discharge voltage. So only about half of the voltage you put in do you get back out if you run it at these higher current densities. Here are about 6,000 amps per meter squared. And that's all I have for you today, and I look forward to discussing this material with you in class.